Hello, welcome to this lesson looking at Kirchhoffs laws and resistance. Now in today's lesson, which is suitable for A-Level AQA Physics, we're going to be looking at applying Kirchhoffs laws to electrical resistance, which is found in the third unit of Paper 1, Electricity. Now in this particular lesson, we're going to be focusing upon understanding how to calculate resistance in series for DC electrical circuits, how to calculate resistance in parallel for DC electrical circuits, then apply these calculations to a variety of different applications, which links in to the following part of the AQA A Level Physics specification. Now, previously we've looked at Kirchhoffs circuit laws. Now, basically, the Kirchhoff circuit laws are the laws which govern all electrical circuits, and all electrical circuits must obey these principles. They're basically the laws behind all modern electrical circuits. Now, in 1845, German physicist Gustav Kirchhoff described two laws. Now, in electromagnetic fields, these laws are generalizations of Ohm's law linking to the conservation of energy. Now, if we apply Kirchhoff's laws, Kirchhoff's rules, to electrical circuits, then we can understand the quantities of different values in the circuit. So, Kirchhoff's first law is the law of charge conservation. Basically, charge has to be conserved in an electrical circuit. Now, we looked at this at GCSE because we said at GCSE that the current is the same throughout a series circuit, because it's a fundamental rule of the universe that charge cannot be created, charge cannot be destroyed, which is previously discussed in particle physics when you looked at conservation laws. Now, Kirchhoff called this Kirchhoffs First Law or Kirchhoffs Junction Law. Now, again, like we said, it's the application that charge cannot be created, it can't be destroyed in a circuit. Now, the rigorous definition of the law would be that the sum of the current into a junction equals the sum of the current out of the junction. But we can split this law into three separate ideas in electrical circuits. Part 1, that at any junction, the total current leaving the junction is equal to the total current entering the junction. Now, a junction, by the way, is defined as a place in the electrical circuit where the circuit has more than one possible path. So in this example, the total current going in is 6 amps, and the total current leaving the junction 6 amps, but it's split 3 and 3 over 2 paths. So as a result, the total current entering the junction equals the total current leaving the junction. But the current doesn't have to split equally the junction. Actually, current splits as an inverse of resistance. So in DC circuits, current and resistance are inversely proportional. And you've always got to remember this rule. That's because the more resistance there is, the more impedance there is to charge flow, so the current is lower. Now, if you want to consider it mathematically, consider the equation you covered at GCSE. Current equals potential difference divided by resistance, or I equals V over R. So if we have a constant potential difference, a constant V, we can then pop in a proportionality constant K, so I equals K over R, which indicates to us that I and R must be inversely proportional. Now, as we said before, if the resistance in each path is the same, the current will split equally. However, if one path has double the resistance of the other path, it's going to have half of the current. And similarly, if the resistance on one path is triple compared to the other, the current on that path will be a third of the other. Now, to work this out mathematically, you work out the proportion of the resistance found on each side, then use this to find the split. So the first step is to work out the total resistance afterwards, so 40 ohms in this example. You then find out the proportion of resistance each path takes. So the upper path takes 30 over 40, or 3/4. The lower path takes 10 over 40, or 1/4. So to find the current in each path, you multiply the current going into the junction by the missing proportion. So because path 1 takes 3/4 of the resistance, you multiply by the missing proportion, which is 1/4. So it's 12 times by 1/4, which is 3 amps. Now that's, like we said before, because resistance and current are inversely related. Now you should always, when you're checking your answers, have a logic check. Now the logic check in this example is that the total current going into the junction must equal the total current after the junction, and the higher the resistance of a path, the lower the current it should have. Now the second part of Kirchhoff's first law is that the current entering a component is the same as the current leaving a component. So components do not use up current. It's assumed that all mobile charge carriers pass through a device. No charge carriers get deposited into the device. No charge carriers change speed. That's the second part. The third part is that the current passing through 2 or more components in series has to be the same through each component. So the rate of flow of charge through each component is the same at any instance. So all the charge carriers are passing through the device. No charge carriers are being deposited into the device. No charge carriers are changing speed. So it's assumed basically that in a circuit wire line, there's no special place. This wire is completely uniform. The current is the same all the way along. So just to clarify, the Kirchhoff's first law, the conservation of charge, is that at any junction in a circuit, the total current leaving the junction is equal to the total current entering the junction. That the current entering a component is the same as the current leaving the component. Components do not use up current. That a current passing through 2 or more components in series is the same through each component. So the rate of flow of charge through each component is the same at any instance. Now, we've demonstrated that before, like we said at GCSE, because in one complete loop, in one series circuit, current is the same in every position. Now, we can link Kirchhoff's first law to actually work out the EMF of multiple cells in series or parallel. Because if you consider a cell in series, each time charge, such as an electron, but any charge carrier, passes through a cell, it will receive an EMF, an energy per charge. Now remember, the charge at each point in this particular circuit, because it's one loop, because it's a series circuit, is the same. So there's an equal charge going through each cell. So the energy per charge received at each cell is going to be the same. Now the adding of more cells in series increases the energy per charge of the charge carrier, because each time a charge carrier passes through one of these cells, it'll have an increase in EMF. So basically, adding more cells in the circuit increases your EMF into the circuit. So basically, mathematically, the total EMF is equal to the EMF of each individual cell in series summed together. But if we consider the cells in parallel now, each time a charge passes through a cell, it will receive an EMF, an energy per charge, but at this time, we've now got a junction. So the charge carriers are going to split when they enter the junction. So if their cells are identical, the charge carriers will split equally because there's equal resistance. Now, again, EMF is only given to the charge carrier when it passes through a cell. Now, in this instance, it'll only pass through one cell because the charge carriers have splitted the junction. So each charge is only passing through a cell once here, so it'll only receive an EMF or energy per charge once. So the effect of adding more cells in parallel doesn't change the energy per charge of the charge carriers in the circuit because it'll only still pass through one cell. So basically, adding more cells in parallel does not change the EMF of a circuit. So in this example, the total EMF is equal to the EMF of one cell, which is equal to the EMF of the second cell. So it's just the same value. Now, Kirchhoff's second law considers not the conservation of charge, rather it considers the conservation of energy, which was shown in GCSE with a series circuit, because as you'd know in a series circuit, the EMF provided by the power source equals the PD coming out of the circuit via the light bulb in this particular example, because it's a fundamental rule of physics that the energy per charge going into the circuit was equal to the energy per charge going out of the circuit. Now this is called the second law, or the voltage law, or the closed circuit law, or the loop law. And again, it's based on the principle of conservation of energy. Now, in this law, basically the algebraic sum of the potential differences in any loop must equal 0, i.e. the circuit is a closed system. The circuit is a closed circuit, which you can write with that particular notation. Now, it means that if you're given a complex circuit in a question, you've got to divide it into many closed circuits, i.e. loops. Now, to understand the second law, we've got to define some previously understood concepts in circuits. So, any source of EMF, like a cell, or an AC power pack, or a battery, is an EMF source. It is something placing energy into the circuit. All of these components place energy into your circuit. They cause the potential in the circuit to rise. Potential just means energy. Now, you've also got potential difference outputs, like bulbs or motors or heaters. And at these particular parts of the circuit, energy is being transferred out of the circuit. So all these components take energy out of the circuit. So we call them potential droppers. So you've got potential risers and potential droppers. Now, in one electrical loop, we consider that a closed system where energy cannot be created, energy cannot be destroyed, only transferred. My apology there. So basically, in one closed loop, the total EMF in equals the total PD out. Now again, like with current, the potential difference doesn't have to split equally, okay, because each device has its own resistance. Now the potential difference across a device is directly proportional to its resistance. So in DC circuits, the potential difference and the resistance are directly proportional, because the greater the potential difference through a component, the greater the energy that passes through it per charge, the more resistance it generates. So if we consider the equation V equals IR from GCSE physics, for a constant I, which is the case because it's a series circuit, we can put the constant proportionality K into the circuit. So we can say V equals KR, which shows V and R are directly proportional. So what that means is, if one output had double the resistance of the other output, it would have double the potential difference of the other output. So if one output had triple the resistance of the other, it would have triple the potential difference across it. Now again, how do you work these particular values out? Well, you work out the total resistance found in these outputs, which in this example once again is 40 ohms. You then find the proportion of resistance each output takes. So the left bulb takes 30 over 40 or 3/4. The bulb on the right takes 10 over 40 or 1/4. You then, to find the PD in each output, multiply the EMF by not the missing proportion this time, but by the actual proportion. So the left-hand side bulb will be the EMF, which is 12, times by the proportion of resistance it takes, 3/4, so you get 9 volts. Now that, if you want to check your logic, is the EMF in should always equal the total PD out, and the higher the resistance of an output, the more potential difference it has. Now again, just to clarify, these are only for DC circuits, not AC circuits. So any laws you might have learned regarding potential difference and resistance for a transformer don't apply here. Now, like the other law, we can apply this second law to some different contexts. So, part 1. For two or more components in series, the potential difference across the components is equal to the sum of potential differences across each component. So, V source equals V1 plus V2. Now, just to clarify, in all these rules, we're assuming there's no internal resistance. The only resistance found in this circuit is in the wanted outputs of your circuit. So basically, energy cannot be lost anywhere in the circuit except the output devices. Now, the second rule is that the potential difference across components in parallel is the same. That's because each loop can be considered its own different closed systems. The loops are supplied with identical amounts of energy per charge from the EMF source. So the more loops connected to the EMF source, the more the total energy supplied. In the case of a battery, this would make a battery drain faster, so that is the issue with putting components in parallel circuits. The third law, or the third part of the law I should say, my apologies, is that for any complete loop of a circuit, the sum of EMF going in is equal to the sums of the potential drops around the loop. Now again, in the EMF will be divided into different potential differences. So we call this setup a potential divider. A potential divider is achieved if you have more than one PD output in an electrical loop, because it will split or divide your potential difference between more than one output. Now, like we said before, the split does not have to be equal. The higher the resistance, the greater the potential difference it takes. So the 3 times as much resistance, 3 times as much potential difference. So just to clarify, for 2 or more components in series, the total potential difference across the components is equal to the sum of the potential differences across each component. The potential difference across components in parallel is the same, and for any complete loop of a circuit, the sum of EMF into a circuit is equal to the sum of potential differences out of the circuit. So, those were Kirchhoff's laws of electrical circuits. So, we're going to now try and apply this to the concept of resistance. Now, resistance is a measure of the impedance of electrical current in a circuit. It's caused by the collision of mobile charge carriers with the metal ions of the conductor. Resistance is directly proportional to potential difference in a DC circuit, but it's inversely proportional to the current through an output. Now, when we're designing or analysing circuits, we can have complex combinations of resistors. Now, to perform calculations with this circuit, so say for example, you wanted to find a suitable fuse to protect the outputs of the circuit, it's easy to try and find a value for the total resistance of the circuit instead of just dealing with individual resistors. Now, we call the total resistance of a circuit the equivalent resistance, because it's equivalent, okay, to the complex combination of all the different resistors. Now we can calculate the equivalent resistance for series and parallel circuits using Ohm's law and the previously discussed Kirchhoff's laws. Now that's a very, very, very important skill, because it allows you to work out the total resistance of a circuit to look at the overall action of the circuit. Now let's consider a series circuit first. So like we just said before, if we have 2 or more resistors or any outputs connected in series with each other, the current through this particular loop will be the same. So I from the source will equal I1 plus I2 plus I3, okay, which is Kirchhoffs First Law. Okay, but if we consider the potential difference, we've just said from Kirchhoffs Second Law that EMF in must equal PD out. So as a result, the potential difference will split between the outputs. So V from the source will equal V1 plus V2 all the way to Vn. So if we know that resistance is potential difference over current, which is the basic equation of resistance from GCSE, we can then say, well, V total over I total equals resistance. Now we can then say V1 over I plus V2 over I plus V3 over I. Now because I is a common denominator, okay, so it can then be factorized into the equation. So we can therefore say V1 plus V2 plus V3 over In. So therefore, we can then simplify this to say the total resistance, the equivalence resistance, is equal to R1 plus R2 plus R3 plus Rn. Now that makes sense to us, because the more resistors in a row, the more collisions between charge carriers the metal ions, the more resistance. So that increases the impedance of the current, it gives you a greater total resistance. So in a series circuit, the equivalent resistance is always larger than any single resistor. So in this particular example, you have 3 resistors in series, a 10 ohm, 20 ohm, and 15 ohm. So the equivalent resistance is 10 plus 20 plus 15, which is 45 ohms. You just add the resistors together. So in this example, we've got 20, 30, and 40 ohm resistors in series. You add up all 3 and you get an equivalent resistance of 90 ohms. Now as a logic check, we said the equivalence resistance is larger than any single resistor. So as a result, 90 is bigger than 20, 30, or 40, so it's likely to be right. Now, let's consider Kirchhoff's laws when our resistors are no longer in series, but they're in parallel. Now we said that if 2 or more resistors are connected in parallel, the potential difference across each one is the same as they're in their separate systems. They're in their separate loops. So V equals V1, which equals V2, which equals Vn. That's Kirchhoffs' second law in action again. But the total current is divided between the branches because it's a junction now. And we can say that the total current going into the junction equals the total current going out. So I from the source is equal to I1 plus I2 all the way to In. That's the first law of electrical circuits. Now, like we said before, resistance equals potential difference over current, which is the basic equation of resistance from GCSE physics. So now we can say V total over I total is your resistance, but now it's not the denominator, which is the common term, it's the numerator. So when you factorize that, you're getting Vn times by 1 over I1 plus 1 over I2 plus 1 over I3. So that works through to be 1 over the equivalence resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over Rn, which can be written as that. Now, this makes sense, as the more resistors in parallel, the more possible paths the charge carriers have to travel down, so it's far less likely we're going to get metal ion charge carrier collision. So, in fact, the resistance lowers because there's more paths for the charge carriers to travel down. So this means that the equivalent resistance is smaller than any single resistor. So how do you work it through? So basically, you find out your values in parallel. So we've got 10, 20 and 15. So we'll do 1 over 10 plus 1 over 20 plus 1 over 15. Find the common denominator in these terms, which is 60 in this example. Change the denominator to the common denominator, and then we've now got 6 over 60, 3 over 60 and 4 over 60. So now we can add the numerators of each resistor whilst keeping the denominator the same. So we've now got 13 over 60. Now you can use your calculator if you wish. If you don't like to do a bit of mental math, it's completely fine to use your calculator to do this. Okay, but after you've done this, you flip the numerator and the denominator because we're doing 1 over R total. So to find R total or equivalent resistance, you need to flip the values. So 13 over 60 becomes 60 over 13, which is 4.62 ohms. Now again, never leave your value as a fraction in physics because that implies infinite significant figures, which we don't like because we're taking measurements in physics. We don't work with abstract numbers. Now, the logic check in any answer should be that the equivalent resistance in parallel must be smaller than any single resistor. So as a result, let's have a check. So it's 10, 20 and 40. So it's 1 over 10 plus 1 over 20 plus 1 over 40. So you change that to the common denominator, 40. So it becomes 4 over 40, 2 over 40, 1 over 40. You add the numerator to keep the denominator the same, so it becomes 7 over 40. We flip it over, 40 over 7. We don't like to keep it in a fraction, so we put into the correct number sig figs, 5.7 ohms. Logic check, that sounds right because it's smaller than 10, the smallest individual resistor. So, in this lesson, if you've learned in this particular lesson, you should understand how to calculate resistance in series for a DC circuit. You should understand how to calculate resistance in parallel for a DC circuit, and then finally apply these calculations to different examination style questions and applications. Thank you very much for listening to today's lesson, and I hope you've enjoyed learning about resistors in series and parallel.